The Autonomous Emily project includes the use of both a USV and a UAV unit that provides a video feed. The work by Dufek et al. Also allows the UAV to provide positional and orientation information of Emily to the operator using color-based tracking. Despite being able to detect Emily in its video feed, and because Emily is constantly in motion, the UAV needs to make sure the USV does not leave its field of view. We aim to interface current work of recognition and tracking of Emily and to use tracked motion information for optimized UAV camera movements to keep the USV in view at all times. We consider two approaches to keep Emily in the camera's field of view. The main difference of each approach is where Emily should be placed within the frame after camera movements. The first approach places Emily at the center of the frame after reaching a set boundary. The second approach, we call smart placement, considers Emily's current trajectory to optimally place her closer to the frame boundaries to allow for more travel distance before additional camera movements are needed. For implementation, the algorithm considers several checks before considering any camera movements. Emily must be moving outward toward the frame boundary, or in other words, away from the center of the frame. Also, a rectangular boundary is set which determines when to send commands to the UAV when Emily crosses it. For the smart placement method, the destination point of Emily's new placement within the frame is calculated by projecting a line based on Emily's heading vector and finding its intersection to the boundary. The final placement of Emily is given a buffer region to give extra room for the camera to stop before reaching the boundary. If Emily's path changes during camera movements, this can cause issues as Emily may not reach the destination point as expected. When this occurs, we calculate a new destination point based on Emily's current positional and heading information. Testing was done using a photokite drone within a lab setting. The tracked object was handheld and manually moved within the video feed. We conducted a comparative study with both techniques using direct movements towards each side of the boundary at different angles. We measured total number of UAV commands sent, distance available to travel after camera changes, and time taken for gimbal rotations to complete from start to end. Our results show that although the center placement technique has short gimbal movement times to reach a stop, the distance left for Emily to travel after reaching the center is much shorter in comparison to the smart placement method. Overall, both techniques take a similar amount of commands to reach its destination. More complex paths would result in additional commands to accommodate additional destination calculations. For future work, we want to consider Emily's speed to control boundary size and gimbal movement speed. In addition, an additional boundary with the current boundary can reduce the number of commands sent as calculations are not needed if Emily is already close to the center of the frame. Testing with the USV itself and with more complex paths is still needed and should be conducted in an outdoor environment where Emily is intended to be used.